All right, this is a continuation of the test review videos. This video will cover problems 6, 7, and 8. So a machine is set to fill Coca-Cola cans with Coca-Cola. Suppose the amounts per cans forms a normal. That's really key. If I see that, I'm probably working with the normal distribution with a standard deviation equal to 0.03 and a mean of 12.05. So my mean in this case, 12.05, standard deviation is 0.03. What percent of the cans will have less than 12 ounces? So we always need to draw our picture. A picture eliminates a lot of errors. So this goes to positive infinity, this goes to negative infinity. They tell us our mean amount, our average amount is 12.05. And they say we'll have less than 12. Well, 12 is, remember, this bottom part is a number line. So 12 is going to be below it. So 12 is here. And then they have the keyword less, which means I'm shading off to the left. All right, so I'm shading off to the left. So I want the norm. And when you're working with the normal, we'll never use a PDF. It'll always be a CDF. Norm CDF, lower bound, which is negative infinity. This is my lower. My upper bound, the highest part that I shaded, which is 12. My mean, which in this case is 12.05. Sorry that this is going uphill the way it is. And the standard deviation, which is 0.03. All right, so we're going to type that into the calculator. Second vars, normal, CDF, negative 99999. Look, fill the screen up. I usually put about 10 of them in there. Upper bound, 12. My mean was 12.05, and my standard deviation was 0.03. And I find out that less than 5%, so 0.0477, and remember, we always want to go to 4 decimal places, equals 0.0477. So less than 5% of the cans will have less than 12 ounces. So about 95% will have more than 12 ounces, all right? Which is good because that's what they advertise, 12-ounce cans. So find the following probabilities and sketch the graphs. Well, here we're working with z-scores, all right? Now, please remember, anytime you're working with a z-scores always have a mean of 0 and a standard deviation equal to 1, right? Very, very important. And by the way, it should have said that this is normal, but these are normal. It's the only thing we know how to do. So at this point, the mean is 0. And they said probability that z is greater than negative 1.06. Well, negative 1.06 is on below 0. So somewhere here, but it says greater, so I'm shading up this direction. So I'm shading up to positive infinity. So when I go to the calculator, it's going to be a norm CDF. My lower bound, I started at negative 1.06. My upper bound went to positive infinity. My mean is 0, and my standard deviation is 1. Please remember, the mean is 0, standard deviation 1, because we're working with a z-score. So this is lower, upper, mean, standard deviation. Second vars, normal, second vars, normal, CDF. Lower bound, negative 1.06. Upper bound, load that up with about 10 nines or until you get tired. Mean was 0, standard deviation 1. And once again, remember, all z-scores have a mean of 0 and a standard deviation of 1. So this is 0.8554. Once again, 4 decimal places. Here, we want a z-score between 1.06 and 4.0. All right. Well, I know 1.06 is above 0, so I'm going to draw that here. And I know 4 is somewhere up here, okay? So I'm looking for this area. So once again, norm, CDF, the lower is 1.06, the upper is 4.0, the mean, I should put a U there for upper, the mean is 0, because all in the standard deviation is 1. Please remember, once again, all z-scores have a mean of 0 and a standard deviation of 1. So positive 1.06 all the way to 4. And we're at 0.1445. I'm going to check that value one more time. Second var is norm CDF, 1.06, upper is 4. That's great. Everything's done right. Perfect. Okay. Number 8. The heights of male adults are normally distributed. Hey, there they go. They told us it was normal, so I'm not using a geometric or binomial. Mean of 1.7 and standard deviation of 0.02. So mean is 1.7, standard deviation is 0.0 or 0.2, not 0.02, 0.2. What percent would you expect to have a height between 1.4 meters and 1.6 meters? So let's draw a picture. All right. So our picture is going to look like this. Mean is 1.7. We have 1.6 here, and somewhere down here is 1.4. All right. So I'm looking for this area. This is my lower bound. This is my upper bound. So this is going to be a norm CDF. Lower is 1.4. Upper 1.6. Mean 1.7. Standard deviation 0.2, because we're working with actual values this time. All right. Second vars, norm CDF 1.4, upper 1.6, mean 1.7, standard deviation 0.2. So 1.4, 1.6, 1.7, and 0.2, that matches, should be good. Press enter, and we end up getting 0.2417. I know I moved that away pretty quickly, so I'll put that back up on the screen for just a second. So 0.2417, 4 decimal places. What is the likelihood that they are taller than 2.0 meters? So once again, we go back and we redraw this. 1.7 and 2 meters is here. And we're shading up, and we're shading up to positive infinity. And you're like, well, no one's infinity. And it's like, well, that's the part that's kind of theoretical. So this is my lower bound. This is my upper bound. So this is going to be a norm CDF. And the lower bound on this case is 2. The upper bound is positive infinity. My mean is 1.7. And my standard deviation is the same 0.2 as we had before. So second vars, norm CDF, lower bound's 2, upper bound is infinity, which we just fill the screen up with a bunch of 9s, mean of 1.7, standard deviation 0.2, and I end up getting 0.0668. So almost 7%, or about 6.5%, are taller than 2 meters. What is the likelihood that someone is shorter than 1.2 meters? All right. (1.2) lower, and they said shorter, and so we're going to negative infinity this time. So this is my upper, this is my lower. And this is norm CDF, negative infinity, up to 1.2, mean of 1.7, standard deviation of 0.2. Second bars, norm CDF, negative infinity, upper 1.2, mean of 1.7, standard deviation 0.2, and I get 0.0062. So 0.0062. So less than 1% of the population. So less than 1%. A little more than 0.5% are less than 1.2 meters tall. All right. So that'll end this video.